Hi everyone, I am Sanjeev and I welcome you to 12th lecture in machine learning. So today's presentation is about support vector machine and I will provide complete convex analysis of the support vector machine. So before taking this lecture, you should be familiar with the following terms such as Lagrange multipliers, relative interior of the domain of a function, L2 norm, infimum of a function, affine functions, distance of a point from a line, and the normal vector of a hyperplane. So the underlying problem is a classification problem and we are considering four kind of datasets for this presentation. The first one is a linearly separable dataset. In the case of linear separable dataset, we have the two classes which can be separated through a linear decision boundary or through the linear basis functions. The classes in this case are non-overlapping and therefore we can have 0% training error. In the case of non-linearly separable dataset, the classes are not overlapping, but we need to have non-linear basis functions or non-linear decision boundary to separate the two classes. In the third case, that is a non-separable linear boundary, we will have the dataset where the two classes are overlapping, but the two classes can be separated through a linear decision boundary or through linear basis functions. And finally, the non-separable and non-linear boundary case, we have two classes which are overlapping and we need to have non-linear basis functions or non-linear decision boundary to separate the two classes. So here's the first part of this lecture, general discussion about the patterns and the algorithms, and let's consider the linearly separable dataset, that is linearly separable in a feature space. So suppose these are the two classes, one represented by red dot and one is represented by the blue dot. So as we can see, a decision boundary like this, a straight line drawn like this can separate this data set. So this is a very easy example, and normal algorithms like perceptron learning algorithm, simple perceptron learning algorithm, voter perceptron learning algorithm can easily solve this problem. Even this problem can be solved using least square discrimination. So we don't actually need the support vector machine to separate this kind of data set, that is a two-dimensional data set and that is easily separable. But still, let's begin with this data set. So we have this data set where we have two classes, one is represented by the red dots and second one is represented by the blue dots. So that is, we have training instances or the training data denoted by xn and tn, where xn is a input vector or the input instance and tn is its target value. The tn can take just two values. It can be the negative one, which denotes the blue class, and another one is a positive one, which denotes the red class. There is some mathematical proof or mathematical formulation for choosing these two values and we will see them later. So we have a feature mapping phi, where phi maps the input instance x to a vector in Rk. That is, we have k basis functions for representing our input training instance xn or x. So phi is a feature mapping which maps x to Rk, a vector in Rk. That is, we are having k basis functions. So the value of any training instance is given as y of xn is w transpose times phi of xn plus b, where b is a scalar and w is a vector in Rk, which means that we have the weight vector w which has k components and each component assigns a particular weight to each of the basis function. We have k basis function and we have k dimensional weight vector. So inner product w and inner product of w and phi is equivalent to assigning the weight to each of the basis function. So our target in solving this problem is to find the weight vector W and the scalar B such that all the training instances are correctly classified. So here we have two classes. If yx is greater than or equal to 1, then we say that it belongs to the first class, and if y is less than or equal to -1, then we say it belongs to the second class. So in case of linearly separable dataset, we can use this kind of formulation where we can say that we need to find the weight vector W and the scalar B such that each instance in the class 1 has the value greater than or equal to 1, and each instance in class 2 has a value less than or equal to -1. And decision boundary is given as y of x equal to 0. So we can summarize this whole thing. We have training instances xn whose target value are given as tn, which can take the value -1 and +1. We have a feature mapping phi which maps the input instance into to a vector in Rn. We have the value for each instance given by W transpose times phi of xn plus b, and for positive class we have yx greater than or equal to 1, and for negative class we have yx is less than or equal to -1, and the decision boundary is given as yx equal to 0. So SVM is a maximum margin classifier where the margin is defined as a perpendicular distance to the closest point in the dataset to the line yx equal to 0. So in finding the weight vector W and the scalar B, SVM first finds a point in a dataset which is closest to the line yx equal to 0, and then it maximizes the distance of the decision boundary from this point. So graphically we can represent this. So graphically we represent it in this form. Say we have this decision boundary yx equal to 0 where there is a solution for the dataset that we have considered, that is this linearly separable dataset. So here's a solution using the primal form of SVM, and all these 3 points are the support vectors. That means they are equidistant from the line yx equal to 0, represented by this 0 symbol. This blue line is yx equal to 0, this line is yx equal to 1, and this line is yx equal to -1. So the perpendicular distance between the pink line and the blue line is known as a margin, and SVM tries to maximize the margin, therefore it is known as a maximum margin classifier. So the distance of a point xn, of any point xn from the line yx equal to 0 is given by this formula. Distance of point xn is mod of y of xn over norm of W, where this 2 denotes the L2 norm. So this can be represented, we can remove the mod by multiplying it with Tn, so that Tn y of xn becomes positive, and therefore we can remove the symbol for absolute value of y of xn, and y of xn can be further expanded in this form. So the distance of a point from the line yx equal to 0 is given as Tn times W transpose times 5xn plus b over norm of W. And to maximize the margin, we first find a point that is closest to the boundary yx equal to 0. So to find the point that is closest to the boundary yx equal to 0, we find the minimum over all n, and which is given as the minimum over n Tn times W transpose times 5xn plus b. And once we get this point, which is the minimum, which is at minimum distance from the decision boundary yx equal to 0, we can start maximizing this distance from the decision boundary, and therefore finally we find W and B such that the margin is maximized. So here we can easily analyze that if we represent W as k times W and B as k times B, then the k will appear in the numerator and since this is an L2 norm, therefore k will appear in a denominator and k will cancel out. So we can see that the scaling of the weight vector w and the scalar b with the same scalar value doesn't affect the solution. So using this property, we can set the closest point as Tn times W transpose 5xn plus b equal to 1. That is, we can use this constraint and we want to find the weight vector w and the scalar b such that the distance, that is the minimum distance of any training instance from the line yx equal to 0 is 1. That is Tn times W transpose times 5xn plus b is equal to 1, and therefore we define the constraint that for all training instances Tn times W transpose times 5xn plus b is greater than or equal to 1. So this is the primal form of the support vector machine, that is the linear SVM. We are not utilizing the dual SVM, and we are using the linear basis functions to separate the two datasets. And as we can see, this is a quadratic programming problem, quadratic program with linear constraint. So this objective function is a quadratic function and the constraints are linear in w and b. So this is a quadratic programming problem with linear constraint, and this is a primal form of the support vector machine. So using this primal form, we can separate these two classes, the class represented by the red dots and the class represented by the blue dots. So this is the solution, and these points are the support vector. For these points, this blue point lie on the line yx equal to -1, and these two red points lie on the line yx equal to 1, and this is the decision boundary yx equal to 0. So this decision boundary is a midpoint of this distance, the perpendicular distance from this line yx equal to 1 and yx equal to -1. So as we can see, the solution is quite promising. We are getting 100% accuracy in training dataset, and we can efficiently solve this problem using the solvers such as CVX for MATLAB, CVX Opt for Python, Cplex, and many other tools to solve this problem, this primal problem. So as we can see, when the dataset is linearly separable, we get 100% accuracy on the training dataset using the support vector machine. So this was a very easy example with the problem is two-dimensional and a linearly separable dataset with non-overlapping classes. So to solve such kind of problems, we actually don't need SVM. There are lots of other algorithms like kernel perceptron learning or the simple perceptron learning, voter perceptron learning, least square discrimination. Several algorithms are there to solve this easy problem. It's quite easy problem, and therefore to utilize the complete power of the support vector machine, we are going to consider the linearly separable case with overlapping classes. That is, the dataset, there is a two classes in a dataset can be separated using a linear boundary, but the classes are overlapping. That is, we are going to have some training error. So in the hard margin problem, this problem is known as the hard margin problem because the SVM doesn't allow any of the training instance inside this margin. Therefore, the constraint that Tn times W transpose times 5xn plus b greater than or equal to 0 doesn't allow any of the training instance to lie inside the margin, and therefore this is known as a hard margin problem. But when the datasets are non-separable, that is, we have the overlapping classes, then we need to relax the constraint, and therefore to solve such problem we need the soft margin SVM. So when the classes are overlapping, or when we have no clue about the dataset that whether the classes are overlapping or non-overlapping, we should use the soft margin SVM. So the approach of the soft margin SVM is to relax the constraints. That is, for each of the training instance xn in the dataset, we formulate the constraint as Tn times W transpose times phi of xn plus b is greater than or equal to 1 minus eta n, where eta n is the relaxation variable or the slack variable, with eta n greater than or equal to 0 for each of the training instance. So here's a pictorial depiction of this case, that is the relaxing each of the constraint with the slack variable eta n, with eta n greater than or equal to 0. So here's a dataset. This is actually the solution for one of the dataset that we are going to consider in this presentation. So here's a red class and here's a blue class, and this is the line y x equal to -1, this is the line y x equal to +1, and this is the decision boundary with y x equal to 0. So ideally all the blue points should lie below this line y x equal to -1, that is all the blue points should give the value y of x less than or equal to 1, and all the red points should ideally give yx greater than or equal to 1, with no point lying inside the margin. But since we are relaxing the constraint, we are allowing the points to lie inside this margin. So all the red points above this line yx equal to 1 will have the value eta as 0. So consider any point, even the point lying on this line yx equal to 1 will have the eta n 0, and same is the case with the blue class. The points below this boundary yx equal to -1 and the points on the boundary yx equal to -1 will have the value of eta equal to 0. So all these points which are correctly classified and which are on the margin have the value eta equal to 0. So this was the case for the points which are correctly classified and the points which are lying on the margin. And now let's consider the case when the eta is greater than 0. There is the points which lie inside the margin and the points which are wrongly classified. So first we will consider the points which lie inside the margin but are correctly classified. Such points are the red points between the line yx equal to 1 and yx equal to 0, and the blue points between the line yx equal to 0 and yx equal to -1. So for such points we will have Tn times W transpose phi of xn less than 1, because they lie inside the margin, and therefore y of x will have value less than 1, and therefore to compensate and to satisfy this constraint we will have the value of eta n as greater than 0. So all the points which lie inside the margin but are correctly classified will have the value of eta between 0 and 1. So such points, for example this point and this point, these points are correctly classified but they lie inside the margin, therefore they will have the value of eta between 0 and 1, because they need to satisfy this constraint, and Tn times y of xn is going to be less than 1, and therefore eta will take a value greater than 0. When the eta n becomes 1, we will have the constraint Tn times W transpose phi of xn is greater than equal to 0, and when we have the eta n equal to 1, the point lie on the decision boundary. So all the input instances for which the eta n is equal to 1 lie on the decision boundary, and once the eta n is greater than 1, the points are wrongly classified, because any such point will have the value Tn times W transpose phi of xn less than 0, and therefore we need to have eta n greater than equal to 1 to satisfy this constraint, because we need to have Tn times y of xn to be greater than a certain value, and that value is negative, therefore eta n will have to take a value greater than 1, so that the nth training instance can satisfy the constraint. So as we will see later, SVM is nothing but a constraint satisfaction problem. When we use the when we derive the KKT conditions and the complementary slackness, we will see how SVM derives its sparseness. So here is the overall picture. The points which are correctly classified and the points which lie on the margin will have the value of eta as 1. The points which lie inside the margin but are correctly classified will have the value of eta between 0 and 1, and the points which are wrongly classified will have the value eta greater than 1. So eta allows the points to be misclassified. So therefore this problem is known as the soft margin SVM. So the problem is minimize over w comma b half of norm of w square plus alpha times sum over I from 1 to n eta I, where alpha is a positive scalar and it's also known as a trade-off parameter. This value of alpha is a trade-off between maximizing this margin and reducing the number of errors. As a margin is maximized, the value of eta will increase, and therefore this value of alpha is a compensation, is a trade-off parameter between choosing a large margin and between the less points in a margin. So this is a convex quadratic programming problem because because the objective function is a convex function of the variables and the constraints are linear. So we have the constraints Tn times W transpose phi of xn plus b is greater than equal to 1 minus eta n, and all eta I for I equal to 1 to n are greater than 0. So this is again a primal problem and can be easily solved. And since the dataset is linearly separable, we don't need any kind of kernels to solve this problem, and therefore we can utilize the primal form of the support vector machine. And this was the original separable dataset that we have considered, and this was a solution using the hard margin SVM, and here's a solution using the soft margin SVM. So as we can see, the SVM has further increased the margin. This was a case for hard margin problem, and here's a case for the soft margin problem. And as we can see, the SVM allows some of the points to lie inside this margin, but still it has 100% training accuracy because all points are correctly classified. Now the points are wrongly classified, and these are now the support vectors. This point, all the points that lie inside the margin and all the points that lie on the margin are now support vectors. So here is a non-separable dataset, that is the dataset which is linear separable, but so all the points on the margin and all the points that are inside the margin and all the points that are wrongly classified defines the support vectors. And these are the only points that play a role in the decision making, and we'll see that later when we analyze the kernel form or the dual form of the SVM. So this is the case of non-linear separable. There is a linear separable but overlapping classes, and here there is a solution using the support vector machine, the primal form of the support vector machine. So as we can see, when we have low dimensional problem with linear separable with linearly separable decision boundary, we actually can utilize the primal form of the support vector machine to efficiently solve the problem. But in general, the problem are not that simple, and we may have a huge dimension problem. Say the dimension is 10,000, where it's impossible to visualize the data, and we don't know that the data is separable or not, or is there any boundary, linear boundary or non-linear boundary that separates the dataset, and we don't know whether the classes are overlapping or non-overlapping. So in such cases, we utilize the dual form of the SVM, which uses the Kernel-Trick to solve the classification problem. So as I mentioned, if the dimensionality is very low and it is easy to visualize what kind of features are required, then we can use a primal form of the SVM, because if we can construct the feature vector, then we can solve the primal problem. Even if the problem is non-linearly separable, that is, we have the datasets which are non-overlapping, but we need a non-linear boundary, and if the dimension is quite low and if it's easy to construct the feature vector, then we don't need the dual form of the SVM. The primal form of the SVM will efficiently solve that problem. And third point is that if it's evident that the dataset is linear separable using the feature mapping phi that we have defined, then we don't need to construct any kind of kernel to separate the dataset, because in that case the phi x will exactly classify the two classes, because we have constructed the right set of base functions which can classify the problem. So we can summarize this whole thing is like when the features are available, when we know that what kind of features are going to separate the data set, and if we can construct those features, then we don't need to solve the dual form of the SVM. But when we have no clue about the features that can separate the two classes, then we need the dual form of the SVM, because in that case we have the kernel methods that can efficiently solve the classification problem. So when we have no clue about the features or the degree of the polynomial to separate the two classes, then we can utilize the dual form of the SVM. If the dimension is very large, say 10,000, then it's impossible to visualize the data, and in such cases we can directly use the dual form of the SVM. So here's the second part, Lagrangian dual and the lower bound. So here's the Lagrangian formulation for the hard margin and the soft margin SVM. We can move the constraints to the objective function using the Lagrange multipliers. So we have the Lagrange multiplier lambda and gamma, where lambda is a vector which have the components as lambda i's, where I is from 1 to n, and same is the case for gamma, where gamma is a vector. This gamma is a vector whose components are given by gamma n for n equal to 1 to n. So for the hard margin, it's half of norm of w square minus sum over I from 1 to n lambda I times ti times double transpose times 5xi plus b minus 1. So lambda is a Lagrange multiplier, or also known as a dual variable, and for the soft margin problem it is this, where lambda n is a nth Lagrange multiplier associated with the inequality Tn times double transpose times 5xn plus b is greater to 1 minus eta n, and gamma n is a Lagrange multiplier associated with the inequality eta n greater than or equal to 0. So this is a Lagrangian function. The Lagrange function has a function of w, b, lambda and gamma for the soft margin, and for the hard margin the Lagrange is a function of w, b and lambda, where w and b are primal variable, and lambda and also gamma in case of soft margin are the dual variable or the Lagrange multiplier. So to solve these problems, we will have to derive certain equations which are known as the KKT equations, and now we will derive them. So here we will consider the general optimization problem, a general optimization problem, and not necessarily convex, but for this case we can assume they are convex functions, that is f naught is convex and fi's are convex and hi is an affine function. So the general optimization problem is minimize the objective function f naught subject to constraints that fi's, which are generally non-linear, fi is less than 0, less than equal to 0 for I equal to 1 to m, which is generally non-linear, and hi's which are affine function or the linear equalities, there is hi of x equal to 0, where I is from 1, where I ranges from 1 to p. So the domain D is given as the intersection of the domain of all the constraints, and we denote the optimal value of this problem, we call it the primal problem, as p star. So p star is a optimal value of this minimization problem, this primal problem. So we can introduce the Lagrange multipliers lambda and gamma for the equality, for the inequalities and the linear equalities, that is fi's and hi's, where lambda I is a Lagrange multiplier associated with the ith inequality, and gamma I is a Lagrange multiplier associated with the ith equality. So lambda and gamma are the Lagrange multiplier, and here's a Lagrangian function which is a function of primal variable x and dual variables lambda and gamma. So the L of x, so L is a function of x comma lambda comma gamma, is a Lagrange function, or the Lagrangian is a Lagrangian function, and the infimum of this Lagrangian over the variable x is defined as the Lagrange dual. So the Lagrange dual is a minimum value of the Lagrangian function over the variable x, this is a primal variable, and it's given as g of lambda comma gamma is infimum over all x belonging to the domain of the function L of x comma lambda comma gamma, which is equal to the infimum over all x of f naught of x plus sum over all I from 1 to n lambda I times phi of xi, lambda I times fi of x plus summation over I from 1 to p gamma I times hi of x. So the Lagrange dual or the Lagrange dual function is defined as the infimum value of the Lagrangian function over the primal variable x. So this function is a pointwise infimum of the family of affine functions of lambda and gamma, and therefore the Lagrange dual function is a concave function, and the Lagrange dual function is always a concave function irrespective of the primal problem being convex or concave or any kind of problem. So this Lagrange dual is a concave function irrespective of the primal problem being convex. So this is always the case. The Lagrange dual function will always be a convex, will always be a concave function, and solving the dual problem will always be a convex optimization problem, which we'll see later. So we can summarize this whole thing as the Lagrange dual function is a pointwise infimum of the family of affine functions defined by the variable or the dual variable lambda and gamma, and it's also the infimum value of the Lagrangian function over the primal variable x. So we have a lower bound, that is g of lambda comma gamma. There is a dual Lagrange function, is a lower bound on the optimal value of the primal problem. So this g of lambda comma gamma, which is Lagrange dual function or just a dual function, is a lower bound on the optimal value of the primal problem. That is a lower bound on this value p star. So dual function g of g as a function of lambda and gamma is a lower bound on the primal on the optimal value of the primal problem p star, and this can be very easily proved. We just consider any feasible point. We can assume any feasible point x tilde such that the fi of x tilde is less than or equal to 0 and hi of x tilde is equal to 0. Since this x tilde is feasible point, it will satisfy these two constraints for the primal problem, and therefore if we can construct any lambda which is greater than 0, this lambda, this symbol denotes a point, the component wise inequality, that is each component of this vector lambda is greater than 0. So if all the lambda i's are positive, then this expression, that is lambda I times phi I of x tilde, is going to be less than equal to 0, and this term is going to be 0 since hi is 0. Therefore this expression is less than equal to 0, and therefore if we add f naught, that is the g of lambda comma gamma is defined as infimum over all x f of x naught plus this expression. So therefore we can see that the g of lambda comma gamma is always going to be less than or equal to the f naught of x tilde. So the dual function g of lambda comma gamma is infimum of L of x comma lambda comma gamma over the x belonging to the domain of the function, which will be always less than this value. And if we assume any x tilde which satisfies this constraint, then obviously the infimum value over all x is always going to be less than or equal to any feasible x, and which is always less than f naught of x. And we define the domain of the dual function as lambda greater than or equal to 0, which there's a component wise inequality, that is each lambda I is greater than or equal to 0, and g of lambda comma gamma is greater than negative infinity. If the value of the dual function g of lambda comma gamma is negative infinity, then we will get the trivial lower bound, because for any convex optimization problem, if I want to find the lower bound on the optimal value of the convex optimization problem, I can always say that the negative infinity is a lower bound, because nothing can be less than negative infinity. So to obtain a non-trivial lower bound, we need to have the lambda i's to be greater than 0. So we can summarize the whole thing as such as g of the dual function g of lambda comma gamma defines the lower bound on the optimal value of the primal problem, and the domain of this dual function is defined as lambda greater than 0, and the pair lambda comma gamma should satisfy g of lambda comma gamma should be greater than negative infinite to get the non-trivial lower bound. So here's the third part, the interpretation of the Lagrange multipliers, and this will help in understanding the role of active constraints, that is support vectors, and this will also help in understanding why we formulate a hard to solve primal problem in the dual form. I may digress a little bit from the main track, that is the SVM, but in the end you will find all these things in a compact form. There is a KKT conditions. All these things will be used for deriving the KKT conditions, and we will also analyze how SVM derives its sparseness. So it may seem to you that I am digressing at random, but in the end you will find that all these materials are linked to derive the KKT conditions and to analyze the sparseness of the support vector machine. So here's an indicator function I negative u, which is the indicator function whose value is given as infinity if u is greater than 0, and whose value is given as 0 when u is less than equal to 0. And same is the case for the I naught u, whose value is 0 only if u is equal to 0 and infinite otherwise. So for a constraint primal problem, that is a primal problem which is minimize f naught of x subject to constraint f I is less than equal to 0 and h I is equal to 0. Suppose to solve this primal problem, the variable x need to satisfy these constraints, because if x doesn't satisfy these constraints, then the problem is insolvable, and therefore we can represent the primal form using the indicator functions instead of Lagrange multipliers. So this problem is same as minimizing f naught of x plus sum over all I from 1 to n I negative of fi of x, whose value is infinite if fi violates the constraint, and I naught of hi, where this value is going to be infinite if hi is violate the constraint. So this problem is same as solving the primal problem with constraints fi is less than 0 and hi is equal to 0. Using the indicator functions, we can reformulate this problem. So to solve this problem, the x will have to satisfy the constraints, otherwise the value is going to be infinite. So in other language, we can say that we express infinitely hard displeasure if the fi's or the hi's violate the constraints, and therefore we can relax these constraints using the Lagrange multiplier, and this is what the dual problem is about. So using the Lagrange multipliers, we relax the original problem, we relax the constraints of the primal problem, and we replace it with f naught of x plus sum over all I from 1 to n lambda I times fi of x, where lambda I times fi of x, that is lambda u, is always going to be less than I negative of u, and gamma times hi is always going to be less than I naught of hi, or gamma times u is always going to be less than I naught of u. Therefore, using the Lagrange multiplier, we are actually relaxing the original primal problem. And for the cases where the primal problem is very hard to solve, and like the integer programming problem, we actually relax the constraints, like in continuous relaxation problems. But since that's not a part of this lecture, I'm not going to discuss the continuous relaxation problems, but just to show that the Lagrange dual is actually the relaxation of the constraints of the primal problem. And here, as we can see, if fi violate the constraint, then the lambda I, for lambda I greater than 0, this value is going to be positive. And if hi is not equal to 0, then the gamma I, that is by solving the dual problem, we will get the gamma I that will make this value positive. So instead of expressing infinitely hard displeasure, we are actually introducing the relaxed displeasure, that is, which is not infinite. We can allow the violation of the constraints. So this is what the dual problem is about. When the primal problem is very hard to solve, or or it's insolvable with the given constraints, then we actually derive the dual problem. Then we actually form the dual problem, and we solve the dual problem, and we find a lower bound on the optimal value of the primal problem. So the fourth part of this lecture discusses the Lagrange dual function and the weak duality. So as we know that the Lagrange dual function, or just the dual function g of lambda, is a function of lambda and gamma, there's a Lagrange multipliers or the dual variables, gives a lower bound on the optimal value of the primal problem. So a very basic question to ask is, what is the best lower bound on the optimal value of the primal problem? So to answer this problem, we maximize the dual function. So the best lower bound for the value p star is the maximum value of the dual function g. So to obtain the best lower bound, we maximize the dual function with respect to the Lagrange multipliers, so the dual variables lambda and gamma. So maximize with respect to gamma and lambda, g of gamma and lambda, subject to constraint that lambda is greater than or equal to 0, and any pair lambda and gamma such that the lambda is component wise greater than or equal to 0, and g of lambda comma gamma satisfies that g of lambda comma gamma is greater than negative infinity. Such points are dual feasible, and the optimal dual variable are represented as lambda star and gamma star. These are also known as the optimal Lagrange multipliers, and we assume that the maximum value of this dual function, this maximization problem, is d star. So as we know that g, the dual function, is a concave function, and as we know that maximizing a concave function subject to linear constraint lambda greater than or equal to 0 is a convex optimization problem, because we can always take the negative of g and we can minimize this function. So if g is concave, then negative g is going to be convex, and this problem is equivalent to minimizing a convex function subject to convex constraint, that is a linear constraint. So therefore this finding the lower bound or the dual problem is always a convex optimization problem, and it's convex optimization problem irrespective of the primal problem being convex or not. So the best lower bound on the p star is a maximum value or the optimum value of this optimization problem, and it's d star, and we define the weak duality the condition of weak duality as d star is less than or equal to p star, and optimal dual gap is defined as p star minus d star, which is always non-negative since d star is always going to be less than or equal to p star. And this can be used to find the lower bound of the optimal value of the primal problem, which is hard to solve. The value of d star can be used as the lower bound on the optimal value of the primal problem, and you can see in many of the continuous relaxation problems like SDP relaxation and Lagrangian relaxation problems, you will find that it's almost impossible, or it's very hard to solve the primal problem, and therefore a general approach is to find the best lower bound on the primal problem. So the fifth part of this lecture discusses the Slater's constraint qualification and the condition of strong duality. So we know that the condition of weak duality states that the d star is less than or equal to p star, and when the equality holds, there's d star is equal to the p star, we say that the strong duality holds. This is a condition of strong duality. And we say that the bound is tight, that is the optimal dual gap is 0, that is the optimal value of the dual problem is exactly equal to the optimal value of the primal problem, and therefore the bound is tight, and we say that the strong duality holds. And in general, the strong duality does not hold for any general optimization. It's not necessary that the strong duality will hold, but for a convex problem in general the strong duality holds, but this is not always the case. So for a convex optimization problem, we just minimize the objective function f naught of x subject to constraints, non-linear constraints. Fi is less than or equal to 0 for I equal to 1 to m, or the linear constraints ax equal to b. For such a convex optimization problem, strong duality holds, but not always. And to ensure that the strong duality holds, we have the Slater's constraint qualification condition, and this condition, this constraint qualification condition, or just the Slater's condition, ensures that the strong duality holds for a convex optimization problem. So here's the Slater's condition. Suppose if there's any x belonging to the relative interior of the domain of the function, that is the D, which is the domain of the primal problem, which is given by the intersection of the domain of all the constraint functions. If x belongs to the relative interior of the domain of the function, such that the non-linear constraints strongly holds, that is fi of x is less than 0 for I equal to 1 to m and ax equal to b. If these conditions hold and x belongs to the relative interior of the domain of the function, then the Slater's theorem states that if Slater's conditions hold, that is fi of x less than or equal to 0 for all I and ax equal to b, then the strong duality will hold if the problem is convex. And there is a certain modified condition which states that if some of the fi's are affine, that is fi for I equal to 1 to k are affine functions, then the Slater condition then the Slater's condition becomes fi of x is less than or equal to 0 for I equal to 1 to k, and fi of x is less than 0 for I equal to k plus 1 to m, and ax equal to b. This means that the strong inequality should hold just for the non-linear constraints, and if all the constraints are affine, then the strong inequality need not hold. That is fi of x can be less than or equal to 0 for x belonging to the relative interior of D, and in SVM all the constraints are affine. All the constraints is Tn times W transpose times phi of x plus b is greater than or equal to 1 minus eta n. All the constraints are affine, and when all the constraints are affine, then solving the primal problem is just equivalent to solving a feasibility problem. So the conclusion of the Slater's theorem is that it implies that for a convex function or a convex optimization problem, the dual optimum value is attained when D star is greater than negative infinity. That is, there exists optimal Lagrange multipliers or optimal dual variables denoted by lambda star and gamma star, such that the g of lambda star comma gamma star equal to D star is equal to P star. There is a strong duality holds. This means that if D star is greater than negative infinity, that is, this is only possible when the primal problem is feasible. If the primal problem is a convex problem and if it is feasible, then D star will be greater than negative infinity, and if the Slater's conditions hold, then the strong duality will hold in such a case. And as I mentioned, SVM has all the affine constraints and the objective is a convex function, so strong duality holds for the SVM, because the eta n for the soft margin problem, the eta i's here is a soft margin problem. These eta i's take care of this constraint, that is, due to the eta I for non-separable for the overlapping case, each of the constraint will be satisfied because this value may become less than 1, and therefore eta n will adjust itself accordingly to satisfy these constraints. Since having stated that the strong duality holds for the support vector machine, we can now see the relation between the primal and dual problem. Since the strong duality holds, it means that the optimal value of the primal problem is exactly equal to the optimal value of the dual problem, and therefore solving the primal form of the SVM is equivalent to solving the dual form of the SVM. The only difference is that the primal problem doesn't allow you to use the power of kernels, whereas the dual problem allows you to use the Kernel-Trick, and this is where the dual form of the SVM gains the advantage. So let's discuss the complementary slackness. So here we'll assume that P star is equal to D star, that is the primal optimum value is equal to the dual optimum value, and without and we will not make any convex assumption on the problem. That is, we don't assume that the problem is convex optimization problem. We just assume that the strong duality holds, and since the strong duality holds, f naught of x star is equal to the g of lambda star comma gamma star, where x star is the optimal primal variable and lambda star comma gamma star are the optimum dual variables. And this step follows from the definition of the dual function, which is infimum over all x belonging to the domain of function f naught of x plus sum over all I from 1 to n lambda I star times fi of x plus sum over all I from 1 to p gamma I star times hi of x. And this expression is always going to be greater than or equal to this this expression, since we are taking the infimum with respect to x. Therefore, for any other x, this expression will always be greater than or equal to this expression. And since x star is a feasible point, therefore this expression is 0, and this expression is less than or equal to 0, since fi of x star is less than or equal to 0 and lambda is greater than or equal to 0, which states that f naught of x star is less than or equal to f naught of x star, which implies that sum over I from 1 to n lambda I star times fi of x star is equal to 0. Since the two values are equal, that is f naught of x star equal to g of lambda star comma gamma star, therefore this expression will therefore f naught of x star will be equal to f naught of x star plus sum over I from 1 to m lambda star times fi of x star plus sum over all I gamma I star times hi of x star. And therefore the f naught of x star is common in both LHS and RHS, and this expression is 0, therefore this expression has to be 0. So we can further analyze this expression, and as we know that lambda I star should be greater than or equal to 0, each lambda I should be greater than or equal to 0, that is each lambda I should be non-negative, and each fi should be non-positive. Since the x is feasible point, therefore therefore it shouldn't violate the constraint for the primal problem, and therefore we find that each term in this summation is non-positive term, and therefore each term will have to be 0. As I have mentioned, lambda I star is greater than or equal to 0 and fi of x star is less than or equal to 0, therefore lambda I star times fi of x star will have to be 0. And the above condition is known as the complementary slackness condition, which further states that if lambda I star is positive, then fi of x star will have to be 0, and if fi of x star is less than 0, then lambda I star is equal to 0. Now, having stated this condition, we can go back to the part 3 of this lecture, the part 4 of this lecture, where we have the relaxed displeasure function. So as we can see that if lambda I is 0, then the fi, the corresponding fi, will play no role in the dual problem, and this is how SVM derives its sparseness. Ith Lagrange multiplier is 0 unless the ith constraint is active at the optimum. So if at the optimum, if the ith constraint is inactive, that is if the inequality strongly holds, that is fi of x is less than 0, then the corresponding Lagrange multiplier will be 0, and it means that that constraint plays no role in the optimization problem. Either either putting that constraint or removing that constraint will play no role in the final solution of the optimization problem. And this is the reason for the sparsity pattern of the SVM. It discards all the non-support vectors from the dataset, since the Lagrange multiplier or the dual decision variable for these points is 0. We will see the solution for the decision boundary for making the decision for the new instance x, and we'll see that it involves the Lagrange multiplier corresponding to each of the instances in the training dataset, and for all those instances for which the lambda I or the dual variable is 0 are discarded, and all the support vectors are kept. Since for the support vectors the constraint is active, and therefore the dual variable is going to be non-zero. Therefore they play the role in decision making, whereas the non-support vectors do not play any role in decision making, and therefore they are discarded. And this is why SVM is known as a sparse kernel machine, or this gives a sparsity pattern to the SVM. So here's a final theoretical part of this lecture. We are going to discuss the KKT conditions and the first order conditions for the optimality. This should be KKT conditions and first order conditions. So here are the KKT optimality condition. So here we are assuming that the Fi's and Hi's are all differentiable functions, and we assume that x star and lambda star gamma star defines the optimal primal and dual variable. So since x star minimizes this Lagrangian function L of x comma lambda star comma gamma star, the gradient with respect to the x star should vanish, whether the problem is convex or non-convex, or the problem is general nonlinear optimization problem. For the global optimal value or the local optimal value, the gradient should vanish. So if the problem is convex, then we have a unique solution stating all the conditions that we have derived, including the complementary slackness. We can constitute the KKT conditions. So here are the KKT conditions. The first is that Fi of x star should be less than or equal to 0. That is the optimal, there's the optimum value x star should satisfy all the constraints for the primal problem. Hi of x star should be equal to 0. That is all the affine constraints should be satisfied. The Hi's are affine functions. Lambda star should be greater than or equal to 0. This is because we need to have a non-trivial lower bound. And here's the condition for complementary slackness. There's lambda star times Fi of x star should be equal to 0. And here is the first order condition, that is the gradient at the optimum should vanish. So all these conditions constitute the KKT conditions. And for a convex optimization problem, if the Slater's condition is satisfied, that is if the strong duality holds, that is the primal problem, optimum value of the primal problem is equal to the optimum value of the dual problem, then any lambda comma gamma, there's a dual variable, and any x, the primal variable, if they satisfy the KKT conditions, then they are optimal dual and primal variables. And this ends the theoretical part of this lecture, and now we will use all these conditions to solve the support vector machine. So here's the Lagrangian formulation. We have already considered this Lagrangian formulation for the support vector machine. This is the formulation for hard margin, and this is a formulation for soft margin, where lambda and gamma are vectors, n-dimensional, capital N-dimensional vector, which are the Lagrange multipliers and also known as the dual variables. So first we'll consider the hard margin problem. So differentiating the objective function, the Lagrangian function, with respect to w and b will give us the condition that w is sum over I from 1 to n lambda I times ti times phi of xi, and differentiating with respect to b will give us that the sum over all I from 1 to n lambda I times ti should be equal to 0. So these are the first two conditions. The weight vector is equal to this expression, and here we have the first constraint for solving the dual problem, and the constraint is that sum over all I from 1 to n lambda I times ti is equal to 0. And substituting the value of w in the Lagrangian function, here we can obtain the Lagrangian function with respect to the variable lambda, the dual variable. And here we can use the Kernel-Trick instead of using the inner product, and we can replace this with the kernel function k of xn comma xm, where k is any Mercer kernel. So this is how the SVM uses the Kernel-Trick to solve the dual problem. So we can reformulate the dual problem. The dual problem, to solve this problem, we can just form a vector where this vector beta the components of this vector beta, beta1 to beta n, represents this product lambda n times Tn, and therefore this problem is equivalent to maximizing sum over n from 1 to capital N lambda n minus 0.5 beta transpose times k times beta, where k is a kernel matrix whose components k n comma m defines k of xn comma xm. And in this presentation I have used the Gaussian kernel function. Subject to constraint that lambda I should be component wise greater than or equal to 0, and sum over all I from 1 to n beta I should be equal to 0, where beta I represents lambda I times Ti. Just to form a simple mathematical formulation, I am replacing the lambda n times Tn with beta. This is not replacing the lambda n times Tn with beta and then putting the constraint that beta equal to lambda n Tn. I am just representing lambda n times Tn with components lambda n times Tn with a vector beta, so that it looks this expression looks nice. And here we can easily analyze that this is a convex optimization problem. Since the objective function is concave, we don't need to restate this, since we have already seen that the dual function is always a concave function. So this problem is again a convex optimization problem and can be easily solved. So here are the KKT conditions. The optimal variables will satisfy the following conditions. The first is the feasibility condition. Tn times W transpose phi of xn plus b minus 1 is greater than or equal to 0. Second is that lambda I will be greater than or equal to 0. And the condition of complementary slackness, that is lambda n times Tn times y of xn minus 1 is equal to 0, which states that if Tn times y of xn is equal to 1, that is if the constraint is active, then the lambda n will be greater than 0, and if the Tn times y of xn is greater than 1, that is if the constraint is inactive, then the lambda n will be 0. And here is the decision rule: y of x is equal to sum over n from 1 to n lambda n times Tn times k of x comma xn plus b. And as we can see, if the instance is if the point in the training instance is not a support vector, then the lambda n will be 0 and that point will play no role in the decision making, and therefore that point can be discarded for making a decision, and therefore SVM uses only support vectors to make the decision, and therefore it is known as a sparse classifier, where B can be derived using the complementary slackness condition. We can expand this. Y of xn is W transpose phi of xn plus B, and for and in general this B is not solved using just a single support vector. We solve this expression for all the support vectors for B, and then we take the average value of B over all the support vectors. So this is the hard margin dual SVM, and as I mentioned, if lambda n is greater than 0, it means that the constraint is active, and for such a point Tn times y of xn will be 1, and that is the point will be a support vector. And if lambda n is equal to 0, then the constraint is inactive, and in that case Tn times y of xn will be greater than 1, that is the point is correctly classified during the training, and such a point can be discarded for making further decisions on new instances. This states that the point which lie on the margin is a support vector for hard margin problem. And now we will apply the same steps to the soft margin problem. First we'll differentiate it with respect to W, which again gives the same solution for the W. Then we'll differentiate it with respect to B, and then we get the same constraint, that is sum over n from 1 to n lambda n times Tn equal to 0, and differentiating it with respect to all the eta n will give the condition that negative of eta n, negative gamma, n plus alpha is equal to 0, which states that lambda n is equal to alpha minus gamma n. And as we know, the lambda and gamma are Lagrange multipliers, therefore lambda and gamma should be greater than or equal to 0, and therefore we can and therefore this is the dual formulation for the soft margin SVM. Again, we define a vector beta whose components represents lambda n times Tn. Just to represent it in a short mathematical form, I'm just replacing the variables lambda n times Tn with beta n. So this is equal to maximizing sum over all n from 1 to n lambda n minus 0.5 beta transpose k beta, where k is again a kernel matrix, and lambda n and lambda and gamma should each of the components should be greater than or equal to 0, and sum over I from 1 to n beta I or lambda I ti should be equal to 0, and gamma n plus lambda n should be equal to alpha for all n. And since this gamma n is not appearing anywhere in the in the objective function, we can try to eliminate the gamma from the dual formulation of SVM, and by utilizing the fact that lambda n plus gamma n is equal to alpha and gamma n is greater than or equal to 0, we can replace these constraints with a single constraint that lambda n should be from 0 to alpha. And here also we can see that the gamma n doesn't play any role in the decision making, and therefore replacing this constraint with lambda ranging from 0 to alpha is quite useful. So this is a dual formulation of the support vector machine for soft margin support vector machine. So again, the KKT conditions states that number 1, the feasibility condition, all the constraints should be satisfied and all the eta n should be greater than or equal to 0. This is the primal constraint. All the Lagrange multipliers should be greater than or equal to 0, where there is a component wise inequality, each of the components should be greater than 0. And here's a complementary slackness, which states that lambda n times Tn times y of xn minus 1 plus eta n is equal to 0, and gamma n times eta n is equal to 0. And this is a solution, and B is derived using the support using the complementary slackness, where B is where we derive B for each of the support vector, and then finally we take the average over all the support vectors. So again, by complementary slackness, if lambda n is greater than 0, it means that the constraint is active, since in that case W transpose times phi of xn plus B will be exactly equal to 1 minus eta n, that is, the constraint is active, and for such a point Tn times y of xn is less than or equal to 1, and such a point is a support vector. So the first case is that if the lambda n is greater than 0 and if the lambda n is less than alpha, which means that the gamma n should be greater than 0, since lambda n is equal to alpha minus gamma n, therefore gamma n will have to be greater than 0, which states that eta n is equal to 0. And if eta n is equal to 0, it means that the Tn times y of xn is equal to 1. It means that such a point lies on the margin, and therefore such a point is a support vector. And the second case is that if the lambda n is equal to alpha, in that case the gamma n will be 0, and for such a point the eta n will be greater than 0, and such a point can either lie inside the margin or can be misclassified. So such a point is either lies inside the margin or is misclassified, hence it is also a support vector, as it will play a role in the decision making. So for such a point Tn times y of xn is less than 1, and it is also and the constraint is satisfied, that is Tn times y of xn is equal to 1 minus eta n. So finally we can discard all the non-support vectors from the dataset, and we can just keep the support vectors, since we need the lambda n corresponding to the support vectors, and for non-support vectors the lambda n will be 0. So if the lambda n is 0, it means that the gamma n is greater than 0, or gamma n is equal to alpha, which states that eta n is equal to 0. Then by complementary slackness, for such a point, Tn times W transpose phi of xn plus b is greater than 1. So such a point is correctly classified and doesn't lie on the margin. So here is a non-linearly separable dataset which has non-overlapping classes, and we will compare the results of SVM and the kernel perceptron. I have discussed the kernel perceptron in lecture 11, and you can go back to the kernel perceptron lecture and download its code. So here's the solution for the kernel perceptron learning algorithm. Use the Gaussian kernel, and as we can see, the 2 points are misclassified in the blue class. And here is a solution. Use the hard margin dual SVM. As we can see, the training error is 0%, and SVM correctly classifies both the classes, and these are the support vectors. So finally, in the decision making, we can discard all these instances, all these non-support vectors, and we can keep just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11 points for making the decision. So this is the sparsity of the SVM. We just need 11 points to make a decision, whereas in kernel perceptron you can see we need all the points to make a decision. And here is a solution using the dual soft margin SVM, and as we can see, the training error is approximately, I think this point is misclassified, or I think this is correctly classified. So the training error is approximately 0, and these are the support vectors, all the points lying inside the margin and all the points lying on the margin are support vectors. So the dual SVM maximizes the margin, and therefore some of the points lie inside the margin, whereas the hard margin problem, the margin is very small and none of the data points lie inside the margin, since we have the constraint in hard margin that none of the points should lie inside the margin, whereas in soft margin we can allow some points to be misclassified, or we can allow some points to lie inside the margin. So here is a non-separable dataset, that is, it has overlapping classes, and therefore we will use the dual soft margin SVM to solve this problem. And here's the solution using the dual SVM. So this is a decision boundary for this problem, and as we can see, the SVM has performed quite well in this problem for separating the two classes. So now let's consider an example. So let's make a data set. So I'm using 100 instances in the class 1. And I'm using 100 instances in class 2. So I'm here considering a separable dataset so that we can analyze both the hard margin and the soft margin SVM, because in the non-separable dataset only the soft margin can be analyzed, since the hard margin will be infeasible since the constraints will be violated. So I'm enabling the the hard margin SVM as well. So the first step is to normalize the data set. So this function will normalize the data set. So as we can see, the scale are from negative 0 to 0 20 and 0 20, and after normalizing the scale will change. So the dataset is normalized, and this is the result for soft margin SVM, and this is the result. That was the result for hard margin SVM, and this is the result for the soft margin SVM. So the scale is from negative 2.5 to 2, negative 2.5 to 2, and let me make the scale same for all the. So the scale are same in this case. So this is the result for the soft margin SVM. As you can see, now the points lie inside the margin, and the training accuracy is 100%. Since the dataset is separable, so therefore the training accuracy is 100%. And here's the result for the hard margin. So this is a data set, this is a soft margin, and this is a hard margin, and this is a soft margin SVM. So as you can see, some of the instances lie inside the margin, but the training error is still 0% since the data set is separable. So that's all in the SVM. Thank you for watching. I am Sanjeev from searching.com. Thank you.